Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Okay, so this is section 4.5, Classical Synchronization Problems. Now, if you read this iBook, you can skip the section 4.3 and 4.4. So you can direct jump to section 4.5. So in particular, in 4.5, we're going to talk about the dining philosopher problems. Okay, so in this section, we're going to talk about a classical synchronization problem. That is the dining philosopher's problem. Now, in dining philosopher's problem, there are 5 philosophers. 5 philosophers. Okay, each representing a concurrent processes. So you can think about 5 philosophers: P1, P2, P3, P4, and it starts from P0, P1, P2, P3, and P4. Now each representing a concurrent process. Okay. Now these 5 philosophers are seated around the table. Okay. So they're running, and there are 5 forks. Okay, each representing a resource. So these are the shared resources. 5 forks are shared resources: F0, F1, F2, F3, and F4, right? Now these are shared resources. Okay, so then these forks are placed on the table such that each 2 neighboring philosophers share 1 fork. So for example, P1 and P2, these 2 philosophers, P1 and P2, share fork 2. P2 and P3 share fork 3. Okay. Now, each philosopher alternates asynchronously between a phase of thinking and eating. So each philosopher has 2 phases: thinking and eating. When a philosopher is thinking, that philosopher doesn't take any resource. Okay, so the philosopher is just sitting there thinking. Now, when a philosopher decides to eat, in the eating phase, that philosopher is going to pick up the forks around him. Okay, so for example, if philosopher 3, P3, wants to eat, then in the eating state, then philosopher 3 should pick up F3 and F4. So here's a scenario. When a philosopher is thinking, it doesn't require any resources. And while the philosopher is eating, it takes some resources. Okay. And then back to thinking, and back to eating, back to thinking. So for philosopher 2, philosopher 1, you're going to do the same thing. Okay. So that's eating. That's eating. Okay. Every time one of the philosophers is eating, you're going to take, 2 forks. Okay. Same thing for the philosopher 3 and 4. Okay. Okay. So basically, using the definition of critical section, then we can think the eating period phase as a critical section, right? because the critical section is the fragment of a code where the shared resource is going to be used. So you can think about that way. So now, the problem is that if philosopher 3 is eating, then philosopher 2 and 4 cannot eat, because the philosopher 3 is going to take 2 resources that the P2 and the P4 are going to use. So that's why it's a very similar problem as the like a race condition problem we just discussed in section 4.1. So the challenge we have is to prevent a deadlock. So we want to prevent a situation is that when a philosopher is trying to eat but never get a chance to eat, okay? And also we should make sure that if philosopher 2 is eating, of course philosopher 1 and 3 cannot eat. But if philosopher 2 is eating, we should make sure that the philosopher, either philosopher 3 or philosopher 0 or 4 can eat, right? Because philosopher 2 only takes F2 and F3, so it's not taking the F4, F0 or F1, so the other one can eat. So that's kind of the dynamic philosopher's problem. Okay, so as was mentioned in the previous slide, the dynamic philosopher problem is just like a critical section problem. The behavior of each philosopher PI can be represented as a loop that alternates between two phases, thinking and eating. Thinking doesn't require any resource. Okay. However, when a philosopher tries to eat, then you're going to take the forks adjacent to the philosopher. Let's say PI wants to eat. So PI need to pick up the forks on the left, which is FI, and also the forks on the right, which is FI plus 1. So once the philosopher actually successfully picked the two actually forks, then the philosopher can eat. So that's why the implementation for the dynamic philosophy is relatively easy, because the semaphore can actually use to resolve that problem. So now in this case, we can define these 5 forks, which are the shared resources, as semaphores, all initialized to 1. So you have a total of 5 semaphores, okay, all initialized to 1. So in this particular case, Fi going to be initialized to 1. Fi plus 1 is also initialized to 1. These are 2 semaphores. Now let's take a look at the implementation of these semaphore solution. Remember, in the semaphore we defined semaphores and also defined 2 operations, P and Q. These are 2 atomic operations. So when the philosopher PI is working, in a while loop, and when the philosopher is thinking, it doesn't require to take any action, just thinking. Okay, now when the philosopher try to enter the eating state, then that's the critical section. Okay, eating should be defined as a critical section because eating requires the resources, requires 2 forks. Okay, so then before the philosopher PI can eat, it requires to grab 2 forks, Fi and Fi plus 1. So the operation P is used to lock the Fi. So you can call P Fi Okay, so the argument is fi, so fi is going to replace the s. Fi is, remember, fi is 1. Okay, so now you have a p1. Now s, this is 1. Now 1 less than or equal to 0, so that's definitely not true, right? So it's a false. If the while loop is a false, then you're going to quit the while loop and jump to the next statement, which is s minus minus. That's a decrement of value of x. So if s is 1, remember, so after s minus minus, s becomes 0. So after you call the operation pfi, the value of fi is actually reduced to 0. Okay, now same thing for the other operation pfi plus 1. You're going to change the fi plus 1 from 1 to 0. Okay, so then the pi going to enter its eating state. Okay, now while pi is in the eating state, then both semaphore fi and fi plus 1 are 0. So that means if the neighboring philosopher, for example, the philosopher on the right, pi plus 1, try to eat, the pi plus 1 need to grab the forks around, adjacent to pi plus 1. So that includes fi plus 1, right? So now if the pi plus 1 also running its code, so then you're going to call pfi plus 1. Now you find out that fi plus 1 is 0. So that means when pi plus 1 call pfi plus 1, now this is 0, right? So then when it is 0, it's going to be stuck in the while loop. So the pi plus 1 will not continue. Okay, it will be stuck in one of the operation p. Okay, now same thing for the other neighboring philosopher, pi minus 1. So pi minus 1, if pi minus 1 wants to enter its critical section, that means pi minus 1 wants to eat. You're going to also need to grab fi. Now fi is 0, so it will be stuck in the operation p. Okay, so both pi minus 1, pi plus 1, the two neighboring philosophers cannot eat if pi is eating. So this way you can control the whole dynamic philosopher problem. Okay. Okay, so using this semaphore, that it will guarantee that if a philosopher is eating in the eating state, the two neighboring philosophers cannot pick up the forks and eat. So this is good. However, the code that we provide, the semaphore, the code that they're using the semaphore, can lead to the deadlock. Okay, why that's the case? Because all the philosophers can pick up the left forks fi concurrently and then block indefinitely on picking up the right forks. Okay, that's a kind of small chance problem, but it could happen, right? Now, how can we resolve that problem, that issue? Remember that using the semaphore, we cannot solve the deadlock problem. So now how can we deal with that kind of problem? Now there are several approaches we can use to avoid the deadlock problem. Okay. Now I listed two here. Okay, one that requests both forks at the same time in the critical root section. So that means when you pick the fork, you're not going to pick the left fork first and the right fork second. You should make sure that you have to make sure that if both forks are available, then the philosopher can pick both and eat. Now, how can we achieve this in reality? So you can do this by the following approach. So you can pick the left fork, and then we can try to pick the right fork. Now, if the right fork is available, then the philosophy need to release the left fork it's already grabbed. Okay, so that way you can guarantee that only when both forks are available, then the philosopher can eat. That's approach 1. Now, the approach 2, using something called asymmetric approach. So that means one philosopher picks up the forks in the opposite order from all other philosophers. Okay. So now, why this can solve the problem? I'm not going to give you the answer, but give you some kind of clue. Now, why the deadlock happens? We need to discuss this. So now remember, so when each philosophy tries to eat, you're going to pick up the left fork first, right? And then pick up the right fork. Now, deadlock happens when all 5 philosophers try to eat at the same time. So when P0, philosopher 0, tried to actually eat and pick up the left fork, and P1 also tried to eat and pick up the left fork, and P2 pick up the left fork, and P3 pick up the left fork, and P5 pick up the left fork. And then when P0 tried to go to the other side and try to pick the right fork, it's not available because it's already held by P1. And when P1 tried to look at the right fork, it's already, held by P2. So that means you actually get into the situation that each philosopher, each philosopher actually grab the left fork, and they are all looking for the right forks. And unfortunately, no right forks are available. So that's a deadlock situation. Now, we try to break this one using the approach 2. Okay. I'm going to actually assign give you the homework assignment for these, and you need to try to explain to me why the approach 2 is going to solve the problem. Now, of course, there are some more approaches. Okay, one example is that you can only allow 4 philosophers to compete. You just remove one of the philosopher, and why this is working. So just think. Okay, I think that's pretty much all for the module 4. Thank you.